Okay, you probably got a warning that it's being recorded and live streamed. And I'll record it locally as well in case something happens. See if I can disable YouTube chat.
So this is the second of these sessions, third? How long have you been running this?
This is the second FPTalks. So it's a little bigger than last year. So I think that's good news. That's the right direction. Yeah, I don't know. I think it was really helpful last year for, bringing a community together and just making it so that like more people knew about each other. And that's also the reasoning behind the format, right? We're asking for short talks because it's not supposed to be like, present your research in detail kind of venue, right? We want people to be aware of each other, to know what work is going on, and to make connections. Okay, comments are just going to stay on. Can't figure out how to turn that off. I did it last year somehow. Okay, great. And it looks like we've got more people signing into the Slack as well. So that's good. We'll have people doing questions.
Hi.
Hi, Dora. So when you were doing the test, the test run, you were even doing it from the same location.
Yes.
It's the same background.
Yes.
We've got to make sure to finish my morning cup of tea before I start my talk. Okay, YouTube link should be posted on the website now. Well, it'll show up eventually. Oh,
Hi.
Ganesh, I see you're setting up a live stream. Sorry, a viewing party.
Viewing party, yeah, yes.
That's
see how many
that's
people.
my and Ganesh's lab in the background there.
Yeah, and we ordered lunch for the students, so let's see how many show up, at least for the lunch. Hi, guys.
Lunch is a good draw, definitely.
There are some people behind. Marisa is here.
Great.
There are some.
Hi, Zach.
Sorry, is that too bright? Is that okay? Are we? That won't be okay there.
So Ganesh, I'm going to mute you just in case.
Of course.
Okay, I think it's time to start. So welcome everyone to FPTalks 2021. Really excited to kick this off. We've got a lot of people showed up here already, and everyone who's a couple of minutes late will show up really soon. So I wanted to tell you just a little bit about like what FPTalks is about. It's a new venue, so it's good to lay out what our shtick is here. So welcome everyone. I'm really excited for all of the different speakers we have. I think it's an exciting lineup of talks. I think we're going to have a lot of interest. We'll see a lot of interesting things discussed, and we'll make a lot of new connections. And that's kind of the goal here. So this is our second time running FPTalks. Compared to last year, it's more talks. We've made an effort to kind of reach out more broadly into the space of numerics applications, of folks using our tools in scientific computing in all sorts of different places. And so hopefully that also makes for a larger audience, so more people to see this work, and also more people to connect to sort of expand our own collaborations and understandings and perspective of what our field is about. So fundamentally, like the reason we're all here talking about numerics, okay, let's see if that goes away. The reason we're here talking about numerics, about floating point, the reason we work on it or do research in it or apply it is because numerics are important. It's a growing part of computing. There's more and more, as science digitizes, as the humanities digitize, as there are new applications in computer science itself, things like robotics and machine learning, numerical computing is becoming more and more important. And there's also growth and new ideas in our field as well. So there's exciting new number representations that people are interested in. There's new hardware to support for numerical computing. And that makes it an exciting place to be. It also means that we have a lot of opportunity to have some impact, right? So we can, through our work, we can potentially impact a lot of different computing. We can make a lot of computations more accurate if that's what we work on, or we can make it more we can make those computations work faster or better. So here's kind of the theory of FPTalks. We're going to take the theory, the applications of numerical computing, and we're just going to combine that with some kind of like open workshop style atmosphere where we can discuss ongoing work. And the hope is to create this open scientific dialogue. So the goal of FPTalks is to be a venue where we can introduce new ideas from lots of different areas and make those connections and hopefully inspire new interesting work. And even in the last year, we've seen that happen. So I think it's exciting, and hopefully we'll continue running this. So we're organizing FPTalks under this project that's been around for about 5 years or so, called the FP Bench project. And FP Bench was initially inspired by this idea that there was a lot of work going on in numerics, but it was happening in a lot of different communities. There's like the numerical analysis community, there's the high performance computing community, there's communities like graphics that use and apply this work, or robotics. And then there's core like programming languages research on understanding floating point. And these communities weren't interacting that much. So the idea was to try to fix this. And we wanted to fix it by combining two things. First, like common resources for the community to work with. And second, to do some community building so that the people in the communities like knew each other and knew of each other's work and could use that to sort of, inspire further work. So let me tell you a little bit about, what the FP Bench project works on and kind of what resources are available. So I'll start with sort of the software resources. So we've been building up a bunch of different common resources like standard benchmarks. If you've worked on numerics papers, you know that it's often hard to find a good benchmark example to work on. So there's like there's mini apps, but like small benchmarks really didn't exist. So we've gathered a bunch. They've now been used in dozens of papers. And the goal here is to allow fair comparisons to prior work, because if we standardize on a set of benchmarks, it's clear what the strengths and weaknesses of those benchmarks are. It's also just easier to do research. Then on top of those benchmarks, the benchmarks themselves, they might not be in the format you want. So we've built a set of compilers. And those compilers let you do things like, convert your benchmarks to some other format. Maybe that's to C, programming language. Maybe it's to a verification tool like GAPA. Maybe it's just to LaTeX, because you need to publish the benchmark as well. And so these are a bunch of common compilers that can do these transformations. They can also do transformations like loop unrolling or common sub-expression elimination. And the idea here is we can create a bunch of interlinked tools. If your tool supports input from any of the formats that these benchmarks can be transformed in, then they can be used in the output of other tools via these compilers. And then finally, we also write standards to link these things together. So the benchmarks are written in this standard format called FP Core. And that format supports a lot of the normal stuff you'd want. It supports library functions, it supports function definitions, mixed precision computation tensors, basically what you need to describe mathematical computation. So I think talking about these tools in the context of a slideshow is a little weird because the tools are something you use. So let me take a moment to demonstrate what these tools look like. So here's the FP Bench website, and this is our list of benchmarks. So for each of these benchmarks, you can expand them, you can look at them, look at how they're defined. You can see that some of these benchmarks come with additional metadata, like a different form of the computation, maybe a more accurate form that it's supposed to satisfy. And we can search these. So, maybe I'm interested in, specifically these two. Well, I could search for them like this, and I can see sort of a collection of similar benchmarks. But I can also search for other things, like I can search for all benchmarks that have, say, the exponential operator in them. And I can just download all of them. So maybe your tool, you've implemented support for transcendental functions, you want to test them, download all the ones with the exponential operator. Or maybe you're interested in comparing yourself to some tool, so you can download all of the benchmarks used in that tool that cite that tool as a source. So that's kind of how you can use this benchmarks page. And the other thing you can see is that if you open up one of these benchmarks, you'll see that there are links down here to other floating point tools. So if you have a tool that accepts FP core input, or even an input that one of our compilers supports, you can let me know, and we'll add it to the list here so people can easily use your tool, see how it works on the benchmarks. So that's one set of things that we've built. I mentioned these compilers. You can look here about how to install them and use them, but it's pretty simple. You compile from FP Core to any output language, and there's a bunch of languages supported here, both including programming languages, but also various verification tools. And then finally, we've got the set of standards I mentioned. So if you want to implement direct support, what I've been doing is any new tools that I develop, it doesn't really matter, what input format I adopt, so I might as well adopt the standard one. So, implementing support for FP Core and so on. And if you're doing that, feel free to ask on, some of these community forums I'll be talking about in a minute. Okay, so that's one set of things we've been doing. We've been putting together these resources. And of course, we'd love contributions here. If you have benchmarks that you use in your research, or if you're using the compilers, if you want to add to the standard something that your tool needs. So that's one thing we've been doing. The other thing that we've been doing, and this has been a big focus over the last year, is trying to build a numerics community here. So one of these you're already very familiar with, that's the Slack instance. We'll be using that during this conference to ask questions, but it's also a great place to ask quick questions, share recent papers, maybe get help compiling someone else's tool or trying to use it. And to supplement that, we've also started holding these monthly community meetings. So you're all invited. If you're at this workshop, it'll be interesting to you. These happen the first Thursday of every month. And the idea here is to have like a really lightweight and informal way to present demos, to discuss recent work, to show off what you've been doing, or to advertise for events, to look for contributors to a workshop you're running, that kind of thing. And then finally, of course, the sort of the peak of the pyramid here is the workshop that you're all at right now. So I don't need to tell you too much about it, but you can see that we've got sort of a spectrum here between really quick stuff at the Slack to sort of more and more formal stuff. And the idea here is that you can talk on the Slack, you can present your work, you can attend the workshop and get your work more widely publicized. And again, it's all about building a community and building connections between us. Okay, so that's what FPBench is doing. If you want to learn more about that, you can go to fpbench.org. And that's the website that I showed you a moment ago. And there you can find all of this information. So let's talk a little bit about this workshop itself. You're all here, so you all made it. I don't need to tell you about how to get here. There's going to be 20 talks in 5 different sessions, and you can see that there are some breaks in between. Now, since we're all numerics people, you might notice that the schedule I have on this slide, it has a decimal point in it to specify the half-hour mark. And as we know, when we've got decimal values like this, the numerics are a little tricky, but we're going to try to keep to the schedule. We're going to try to make it as low error as possible, avoid approximation here. So these talks, we're going to roughly aim at about 10 minutes per talk. So between these sessions, we're going to have some breaks. And during those breaks, I'm going to keep the Zoom discussion going. You can discuss on Slack and continue the conversation that way. So let's talk some brief logistics before we move on to like the more interesting speakers, the speakers with something numerics related to talk about. We're going to be muting your microphone. So, if you're not speaking, please do that. We're going to be handling audience questions on Slack on the channel FPTalks 21. So I think I have joined most of you to this channel. If you're not in the channel, please join it. And the way it's going to work is that before every speaker, I'll be posting a thread for questions for that speaker. You can ask questions as we go through the talk. And then at the end, we'll try to handle the first couple of questions over Zoom. And if there are questions that are left unasked because we ran out of time, the speaker can just continue to answer those questions in the thread and you can discuss further. Finally, you probably saw a warning when you joined, but this talk is recorded. It's also streamed live on YouTube. So it's out there. You can refer to it to others, send it to your friends and colleagues, etc. Just some quick notes. If you have any kind of questions, Slack is the best way to contact me just because it's the fastest and I have it open on a second screen right here. So you can contact me on Slack. If you have like tech support questions, you can also ask them in the support channel. So that's how we'll be running the conference. I don't want to take too much more of the time. I want to welcome you all here and I want to move on to some of our speakers. So this is the first session, and the first talk is going to be Debasmita. She'll be talking about, she'll be moving us on to the part of this where we actually talk about numerics. So Debasmita, are you ready?
Yeah.
Okay, great. So we're a little ahead of schedule. But this is good. We'll slow down later on. Okay, so let me introduce Debasmita. She's a PhD student at the Max Planck Institute for Software Systems. She's advised by Eva Darulova, who's actually been a part of organizing and helping with FPBench for years and years now. Before her PhD, she got her master's degree in India at IIT Kharagpur, and she's mostly interested in verifying programs that use floating point or other finite precision mechanisms and looking at the numerical uncertainty involved. So Debasmita, please take it away.
Thank you for the introduction. You can see my screen, right? And hear me well? Okay.
Yep.
Hi, everyone. Thank you for coming to my talk. Today, I'm going to talk about our work on conditional floating point verification. This is a joint work with my collaborators from MPI SWS and Joshua, who was an intern with us last summer from University of Rochester. So let's start with an example. Suppose we have two vectors, dx and dy, and we want to compute a dot product of these two vectors. So we write this small function in double precision. And because everything is happening in double precision, it might happen that depending on the values of dx and dy, the result is too large to be represented in double precision, which leads to arithmetic overflow. It might also happen that the round of errors are too large, which causes cancellation. Now, there are several tools available that can handle such programs. So these tools take as input the function, the ranges of the input variables, and then they can compute the round of error at the output. And these tools can also prove the absence of overflow as a byproduct. But in general, these functions do not appear standalone. Actually, these are parts of larger programs. So for example, our dot function is a part of this big linpack program, which has over 500 lines of code. And for these larger floating point applications, the state-of-the-art round of error analyzers that do not handle these kind of programs. So what can we do if we have such a large program? We could do verification. There are several static analyzers like ASTRI and CBMC. These tools are sound for runtime errors, but except CBMC that performs model checking, the tools are doing imprecise numerical analysis, and also they do not check for cancellation. So for example, we used ASTRI on our benchmark, the linpack benchmark, and ASTRI generated arithmetic overflow warning, and it did not check for cancellation. We could also do testing of such a program. So there are several tools available for dynamic analysis, and these tools find actual bugs. However, except the symbolic execution tool, these tools are unsound. So for example, we have used AFLGO, which is a directed gray box fuzzer, on this particular example, and within 1 hour, we couldn't find a bug. However, this does not ensure that there is no bug. So to summarize the current state of the art for larger floating point applications, the tools available are either too imprecise or they do not scale in practice. So we have seen that there are two types of analysis: the static analysis that provides soundness but performs high over approximation. And then on the other hand, we have dynamic analysis that is unsound, but it is much more practical. So in this paper, we relax our soundness guarantees in order to achieve wider applicability. So we aim for conditional verification. And with conditional verification, we get better accuracy than static analysis. And we also get some guarantees that the dynamic analysis cannot provide. So the main intuition behind the combination of these two analyses is that not every part of a program is numerically interesting. So for example, the dot function that I have shown you before is numerically interesting, and we call these interesting parts numerical kernels. The idea is we want to use the standard numerical analyzers on the numerical kernels in order to verify them. However, in order to use these numerical analyzers, we need the kernel input ranges. And our idea here is to use some whole program analyzers that scales well, but performs imprecise numerical analysis to analyze the whole program and infer the kernel ranges automatically. So the main challenge here is to compute kernel ranges automatically as tight as possible. So we are given with the big program, the ranges of the program inputs, and some identified kernels. And we first try to do a static analysis because we want to compute sound ranges. For that, we used ASTREE, which is an industrial-sized abstract interpretation tool. And here our aim is to compute as tight ranges as possible because we want to reduce over approximation. However, if ASTREE cannot provide any useful ranges, it generates -infinity to +infinity ranges, then we move to dynamic analysis, where our aim is to compute as wide range as possible because we want to cover as much actual range as we can. And depending on what kind of analysis we do in the first phase, the ranges are going to be conditional. Now, let us see how we could do dynamic analysis to compute the kernel ranges. So for that, we need this kernel monitor that we instrument before the kernels in the code. So basically, this small code fragment tracks the valuations of the kernel inputs at every iteration. And finally, it just spits the maximum and minimum value that it has been seen for this whole time. So the most naive thing we can do is do a dynamic black box fuzzing. So we implemented the black box fuzzing in our prototype tool Blossom. So Blossom automatically instruments the program and randomly fuzzes the program inputs. And the kernel monitor checks the ranges of the kernel inputs. And finally, after a timeout, it returns the ranges. The range here I show you is an average over all kernel variables. And as you can see, the range is not a trivial range. However, the question is, how much actual range did we cover? Is there some outliers? And we want to find the outliers because generally these outliers create numerical problems in numerical kernels. Now, one might think that a better approach would be doing gray box fuzzing. And we indeed used a directed gray box fuzzer, AFLGO, for this purpose. So we directed AFLGO towards this kernel ranges, kernels, and then first we generated some initial ranges. And then until a timeout, we tried to iteratively broaden the kernel range. But here, as you can see, the ranges generated with AFLGO is quite a magnitude smaller than the black box fuzzing ranges. And our hypothesis here is that this is happening because AFLGO is inherently focused in finding more paths that leads to the function rather than widening the ranges. Now, the question is, can we do better? In our paper, we proposed a guided black box fuzzing, which is focused on widening the kernel ranges. So basically, it uses a feedback loop from every iteration. It first checks whether for a particular valuation, the range of the kernel inputs are increased. So for example, assume cray variable and assume for this particular execution, the valuation of cray is 0.5. And with this valuation, the range of the kernel is increased. Then we keep 0.5. In the next iteration, we try to get the next valuation of cray from the neighborhood of 0.5. And this neighborhood is defined by the radius r. And the radius r depends on the ranges of the program input. So the neighborhood of cray is 0.5 minus r and 0.5 plus r. So basically what we do is in the next iteration, we try to pick some value of cray from this range, assuming that that is again going to broaden the range. So basically this is a simple heuristic, but it turns out that it works very well in finding the outliers. So as you can see here, we actually got some corner cases where for some corner values, the range of the kernel is huge. So let's see how this performed for computing kernel ranges. So we have several benchmarks in our paper. Here I show you only 2 of them, which were the most interesting ones. As you can see, S3 generated infinite ranges. And among the other fuzzing techniques, Blossom's guided black box fuzzing was extremely good at finding the outliers. So this is the result of the first phase. So we generate the kernel ranges. Now let's see how we can verify the kernels. So as I mentioned before, we have several benchmarks from various domains, and they're written either in C or in C++. And the lines of code varied from 31 to a little bit over 2000. And the smallest benchmarks, the arc length and linear SRC, for them, we could use asterisk ranges. So basically, those 2 are fully verified. For the other benchmarks, we could not use asterisk ranges because asterisk generated trivial ranges. For these benchmarks, we did conditional verification. And as you can see, for all of them, we either conditionally verified them or generated cancellation or none or infinite one. So to summarize what I have been explaining until now, in this paper, we propose a 2-phase approach for conditional verification of larger floating point application. It is a fine trade-off between soundness and wider applicability. In the paper, we also show how these ranges can be used to optimize the numerical kernels. For the numerical kernel analyzer, we have used DAISY, and we have done a bit of extension of DAISY in order to check for cancellation, the details of which is there in the paper. And our tool Blossom is publicly available on GitHub in this link. That's all I wanted to say. Thank you for your attention, and I'll be happy to take questions now.
Okay, thank you so much, Debasmita, for the talk. So I've asked Zach to MC the question session so that I can prepare the threads and intros and so on. So Zach will be handling questions.
And just to remind folks, the Slack FPTalks 21 channel will have a thread for each speaker. Please put your questions there during the talk. So one question we have is from Pavel, actually. And through work on projects like Herbie and Optuner, we've noticed that determining input ranges is both essential and also quite tedious for many users. And so Pavel's question is, whether you've seen any impact from some sort of false sharing, where the call sites of some operator, there's 2 different call sites, and you end up with very pessimistic estimates for input range.
So with the dynamic so for static analysis, yes, we can get the pessimistic ranges. For dynamic analysis, whatever ranges we get, we actually do see the minimum and maximum valuations. This is an approximation, of course, because we do not see all the valuations in between the minimum and maximum. So at least the minimum and maximum valuation we do see. So this is not, I don't know if I understood the question correctly, or does that answer your question?
Let me try to elaborate. If you have your example of a dot product operator, right? It's probably used as a utility in many places, right? Yeah. There might be one place in the code where you dot product 2 vectors, and those vectors are both really small. And then in some other place, you dot product 2 other vectors, and those vectors are known to be in the first quadrant. And in some other place, you dot product 2 other vectors. So, it might be better to analyze that program, that operation, that function, as like 3 different functions with 3 different input ranges. Have you seen a lot of that?
Okay. Not really. I mean, we just, with the dynamic analysis, we just tracked the minimum and maximum value. No, we did not do that.
Thanks.
We have another question from Ignacio Laguna, and that's on what input bounds did you use for larger programs such as Lulesh?
We have taken all the benchmarks from various domains. For Lulesh also, there were some input ranges given, and we just used them for the program inputs.
So those just appeared in the benchmark?
Yeah.
Got it. Another question I was curious about, there's this strange success of these sort of dynamic techniques. And so, Herbie's also just sort of based on sampling. One of the things that's interesting with fuzzing, like the gray box fuzzing with AFLGO, is it just keeps getting better and better. So I'm curious if you've thought about, if you give a user a tool that is dependent on another tool and that tool keeps improving, like have you seen that effect, and what is that experience like? One day I wake up and all of a sudden the tool's giving me much better results. Have you seen any issues with sort of stability or predictability of the tools because of sort of underlying technology improving?
So for AFLGO, we only had one particular version of it, and we tried it. And with so the timeout we used was for 1 hour, and with increased timeout, it didn't really matter for AFLGO.
Got it. Yeah, that might be. I think it might be an interesting sensitivity study, almost like, because those tools just keep getting better and better, almost every month or week or whatever. It'd be interesting to see sort of like what direction is that pointing, like where might it end up, and if we could anticipate that, what would happen. But yeah, super cool work. Yeah. So I think with that, we will probably go ahead and set up the next talk.
Yep.
Thanks again, Debasmita.
Thank you.
Yeah, please keep your questions coming in the Slack.
That's right. So yeah, thank you, Debasmita. And if you have another question that sparked, later, maybe as you watch another talk, all of these threads will be around. And one of the benefits of having it in Slack is that you can go back and continue having the discussion. And of course, you can also just send Debasmita a message over the Slack. Okay, so our next talk is going to be from Deevashwer. He is currently a research fellow at Microsoft Research India. And soon he will be a PhD student in computer science at the University of California at Berkeley. So he's broadly interested in security, cryptography specifically, and his work is going to be kind of on the intersection of that with floating point and numerical computation. Please take it away.
Can you hear me?
Yes.
Hello everyone, I'm Devashwer, and in this presentation, I'll be talking about SecFloat, which is a recent work with my colleagues at Microsoft Research. In this work, we bridge the gaps between floating point and secure two-party computation. So let's begin. So the first question is, what is secure two-party computation, which is a term I have in the title. So let's say we have two parties with secret inputs X and Y respectively that have a communication channel between them. The problem of secure two-party computation, or 2PC, is as follows. The parties want to compute a public function f on their secret inputs X and Y without revealing the secret inputs. Now, on the surface, this sounds impossible because evaluating a function without knowing its inputs seems paradoxical, but this is actually possible with the magic of cryptography. In particular, we already know cryptographic techniques for 2PC that are secure. That is, they only reveal the function output and nothing else, and are also complete, which means that any function can be securely evaluated. Since arbitrary functions imply arbitrary programs can also be securely evaluated. Now, let's focus on floating point programs, which are used almost everywhere. In the current situation, if you want to do secure floating point computation, you have two options. The first is to take existing precise implementations and run them with 2PC. This option, however, has horrible performance because these floating point implementations have not been designed keeping 2PC performance characteristics in mind. The second option is to consider the existing work on secure floating point. This option has better performance than the previous one, but the performance is still bad. And on top of bad performance, this option is also imprecise. For instance, there are some inputs for which the math functions, there are some inputs for which the secure floating point output does not match the ideal output in any of the digits. Thus, there exists a wide gap between floating point programs and their secure realization through 2PC. And a consequence of this gap is that applications like privacy-preserving machine learning, which rely heavily on 2PC techniques, have to settle with fixed point arithmetic and its limitations. Our approach to bridging this gap is to design new floating point functionalities which are precise and 2PC friendly. Our functionality for primitive operations are correct, which means that they always output the floating point value closest to the ideal result. And our functionalities for the math operations are precise, which means that they either output the floating point value just smaller than the ideal result or just larger than the ideal result. We verify the correctness of our math functionalities for 32-bit floats through exhaustive enumeration. Overall, our functionalities achieve the same level of precision as Intel's libraries. To assess the performance of our functionalities, we also implement them in a library called SecFloat, which achieves up to 3 orders of magnitude improvement over prior work. And our SecFloat just requires 0.09 milliseconds per sign operation, while the prior best baseline required 130 milliseconds. Thus, SecFloat improves the state of the art in terms of both precision and performance. Now, let's see how we go about designing these functionalities, starting with the primitive operations. Our approach for the primitive operations is to construct these operations by composing secure integer and fixed point building blocks. The important point to note here is that the cost of these secure integer and fixed point building blocks scales linearly with the bit width. So we want to keep the bit width as small as possible so as to keep the 2PC cost low. And this becomes our main guiding principle, and this is exactly what we do, that we, for these primitive operations, we compute the exact floating point result with minimal bit widths and then round to the nearest floating point value. The rightmost column in this table shows the improvement some of our functionalities have over prior state of the art, and you see that the performance numbers are great. But despite these improvements, the cost of the floating point functionalities is still large compared to the fixed point and integer counterparts. Which brings me to one of the central points of this talk, which is that 2PC has very different performance characteristics, which is why the existing implementations fare poorly in terms of performance when done with 2PC. Now, next up is our math functionalities, the design of our math functionalities, which is the most interesting part of this work. Our math functionalities follow the standard 3-step procedure, which is used by all the math libraries. And here, I'll take a simple example of log to the base 2 to explain what these 3 steps do. The first step is range reduction, which reduces the range of the input to a much smaller interval, in this case from 0 to 1. The next step is polynomial evaluation, which evaluates a polynomial approximating the math function on the reduced input. And the final step is output compensation, which adjusts the output of polynomial evaluation to output the functionalities result. And it is easy to see for this simple example of log to the base 2 why these 3 steps work. Another important point to note here is that these three steps can introduce errors into the computation, which is why we have to work with higher precision arithmetic to account for these errors. So far in explaining this three-step procedure, I've explained what is common between existing implementations in SecFloat. Let's see what are the differences. Now let's see what are the differences. The first difference is that existing implementations use double for intermediate computations, but this is expensive for 2PC due to its large bit width. In contrast, SecFloat uses a custom 36-bit floating point representation with 27 bits of mantissa, which is around 2 times better than doubles. A consequence of using this custom representation is that our range reductions become more complex. For example, in the log functionality I showed before, the output compensation suffers from cancellation error, and when beta is equal to -1. And this is not a problem for doubles because they have higher precision, but our custom floating point representation, using our custom floating point representation, the output compensation fails. And so what we do is we change the range reduction so that we don't have to face cancellation errors, and we do this by handling the case of beta equals to -1 separately. Now let's focus on this table on the top right, which I borrowed from a previous slide. And the point I want to make here is that the floating point operations are quite expensive compared to integer and fixed point operation, especially addition. So we want to keep them to a minimum. So the polynomial evaluation step has a lot of these operations, and existing implementations use high degree polynomials, which leads to a lot of these floating points addition and multiplications. So we instead use low degree splines or piecewise polynomials, which have less number of floating point addition and multiplications, but additionally have floating point comparisons. Even though floating point comparisons are cheaper compared to addition and multiplication, they can still become the bottleneck because they scale linearly with the number of pieces. So what we do is we carefully choose the knots so that comparisons can happen on small number of bits. Specifically, we choose a knot such that instead of doing floating point comparison on 36 bits, we can instead do integer comparison on at most 8 bits. which is great for 2PC because we are reducing the bit length and we are also switching from floating point comparisons to integer comparisons. I would also like to point out here that we generate the coefficient for these splines using RDBM's approach, which will be presented later at this event, and I highly recommend that you check it out. Existing implementations also use floating point operations and range reductions, and to further reduce these operations, we only use minimal bit fixed point operations in our range reductions. Now let's see how SecFloat fares against the prior state of the art. And for primitive operations like division, SecFloat is around 17 times better in runtime. For math operations like sign, compared to the precise baseline of taking an existing implementation and running it with 2PC, SecFloat is 3 orders of magnitude faster. And even compared to the imprecise state of the art, SecFloat is 5 times faster. In conclusion, I would like to highlight that 2PC is like a new hardware with very different performance characteristics. And for the same, we have designed specialized floating point functionalities. Our functionalities have large improvements in precision and performance over prior work, and will open source our implementation once our paper gets published. And I would like to end with some direction for future work. So the first point is that we spend a lot of manual effort in optimizing these functionalities, trying smaller and smaller bit widths, and analyzing the trade-offs. It would be great if this process can be automated. The second point is that the 2PC latency also depends on the function depth, and currently our functionalities are quite sequential. So yeah, it would be another great step if we can design precise math functionalities which have lower depth. The third point is that our math functionalities currently have only been verified for correctness for 32-bit floats using exhaustive enumeration, which is an approach which is intractable for 64-bit doubles. So we need new verification techniques to scale to doubles and higher precision floating point representation. And that is it. Thank you for your attention.
Very nice talk. So we've got a few questions here in the Slack, and just remind folks, please feel free to pipe up with more. It seems like a lot of people are kind of surprised on the custom representation, in particular that it's better than doubles. And so better in terms of performance, is that right?
That is correct, yes.
And one question that Santosh was asking, and I guess that comes from custom hardware implementation? Or is it, are you doing it on like stock, x86, ARM, whatever, and just using integer ops to realize that number system?
Yeah, so it's like, so we are not running these things on CPUs. So what we're doing is, I'm talking about, it's like a new kind of hardware. It's actually not a hardware. It's about so we have something called two-party computation, secure two-party computation, which has all these primitives. Like it can, theoretically, it can do anything. And their operations have different performance characteristics compared to CPUs. So it's like a completely new hardware where some things are very expensive and some things are very cheap. For example, additions are essentially free. They have negligible cost, but multiplication gets very expensive for integers. But the flip side is that for floating point additions are quite expensive, but floating point multiplications are very cheap. So there are these like new kinds of performance characteristics, which is why the existing implementation don't fare so well when run directly with 2PCs.
Got it. So I guess one thing, just following up, there are a couple more questions too, but when you switch the number system, that can actually have consequences for application level code, right? I might want to compute something differently in 64-bit versus 32-bit. Maybe I'm going to take more iterations of some iterative technique or something else. So have you looked at sort of the back pressure this creates on the application when you use this custom representation, or have you seen any changes where applications need to be changed to account for this alternate number system?
So currently, what we have done is we have only focused on 32-bit floats for this work, and not considered higher representation like doubles. And in terms of applications, like what we were trying to do is get some precision bounds. And yeah, I haven't seen. So you mean that like using this custom floating point representation for the intermediate operation, what it will do, how it will change? Yeah, I think we have not looked into it.
Yeah, that's super interesting. So just going on, there's some additional questions. So in particular, actually, Pavel, I don't know if you want to ask this verification question. We realize that, for folks in the Slack who aren't watching on YouTube, you're also welcome to ask your question live on air if you feel like unmuting, but no pressure. We can also proxy them if you prefer.
So I'll ask this one live. Yeah, so I was wondering, you talked about a big challenge is verification for larger bit widths. Is that similar to verification for, ordinary library implementations? Is that like the skill set of verifying a new libm? Is that like the skill set of verifying hardware? I know you used exhaustive enumeration. That works great for 32-bit, but I'm trying to see what kind of skills are necessary to take this forward.
Yeah, very much so. I think it's pretty similar. So if you look at our paper, once it gets released, the functionalities, they look pretty similar to what you would see what you would see in a C code, for example. And yeah, I think the challenges are pretty similar. Yeah. So I think it's a very interesting problem for this company.
Just a follow-up question to that. Do you think you'd get a bigger speed up if you had a less accurate function implementation? So it looks like you're going for, up to 1 ULP of error. But if we allowed up to 10 ULPs of error, would that be faster? Would the speed up be bigger or smaller than the corresponding speed up on a regular CPU? Just asking you to speculate.
I think it depends a lot on how far you're willing to go. If you can allow a lot of error, then probably yes. But if you are saying, let's say 4 ULP error, then I don't think it will make that much of a difference. I don't know about what will happen on CPU, but I think for 2PC, I think it will not make that much of a difference.
And it looks like Santosh has a hand up, so we'll switch to him.
Okay, great talk. So I'm just curious, so with 821 custom FP representation, how are you avoiding the numerical errors and still guaranteeing less than 1 ULP error for all inputs?
So it's like we have used different range reductions, which are quite simple. And the trade-off we are paying is we are considering larger ranges. So our reduced ranges are quite large. So for example, for the log to the base 2 example, our range is reduced ranges from -0.5 to 1. So that's pretty big to approximate using splines. And by doing that, so in that particular example, if we were to, since we were using an 8x27 representation, we were running into cancellation errors in one particular case. So we handled it separately so that we avoided.
So just a follow-up to this, right? So if you increase the range, the degree of your polynomial will increase. So likely, it will have inferior performance compared to a traditional RLibm or an Intel library, right? So the performance primarily, this was my previous question. So the performance is just coming from the low-level tricks that you're doing with respect to your 821.7 representation. There are two aspects here, right? There's a 2PC issue coming in, that there is a lot of overhead with a 2PC baseline. And then there is pure computing a less than 1 ULP result performance, right? So what I'm trying to get at, if you remove 2PC stuff, if you just use it as a traditional math library, and now evaluate the performance, what would it look like? Is it still performant, or is it the majority of the performance is primarily coming from reducing the overhead with respect to 2PC computation and custom representation?
Okay, so to answer your question about had we used doubles and so using doubles would require less degree, and yeah, maybe that could have led to better performance. So in that respect, what we do is, so since we have made the comparisons cheaper with respect to 2PC, what happens is you can increase the number of pieces a lot without affecting performance that much. So rather than increasing the number of, increasing your degree, you can still work with this relatively imprecise representation of 8,27 and increase the number of pieces much more and still keep your degree low. So it's for example, if you have, yeah, it's like that. So what we have tried to do is, yeah, I think it will be using doubles. could have led to like, if we were to use doubles in our implementation, I think it will still lead to worse performance compared to what we have right now, but it will not be that much worse because we could use smaller degree in some places.
Okay, and I think so. This is a great discussion. I think with that we are gonna mosey along to keep on time, but this is great. And remember, folks, the threads are there, so please feel free to continue discussing these talks even after the day wraps up. If something occurs to you, tomorrow, make sure to pipe up and tag people. But I think with that we will move on to the next talk.
Yeah. Okay. So yeah, exactly. Let's make use of the Slack. There's a lot more to discuss, I think. So our next talk is by Anastasiia Izycheva. She's a fourth-year PhD student at the Technical University of Munich, and her work is primarily focused on applying programming language synthesis techniques. So she'll be telling us a little bit about synthesizing kernels to low precision. Anastasiia, please.
Thank you for the introduction. Let me share my screen. Okay, can you see my presentation? All good. Great. So my name is Anastasiia, and today I will tell you about the joint work with Eva Darulova and Helmut Seidel on how we synthesize efficient fixed-point kernels. Let's start with an example. Say you have an algorithm that is given 2 points specified by latitude and longitude, and it computes the angle between these points to some plane of reference. And you have some hardware where you want to implement this algorithm on. The question is, how do you implement this kernel efficiently? And here by efficiently, I mean with low running time. Since we are implementing real valued algorithm in final precision, we are inevitably introducing approximations for all numbers. And additionally, if the algorithm has elementary functions like sine, cosine, arctan, those are usually implemented as library function calls. And inside libraries, these elementary functions are also approximate. So we have some noise. Luckily, many applications are designed to be robust with respect to a certain amount of noise. And moreover, most of the time, we don't actually need this algorithm to work for the whole domain of all possible values, but it only needs to work for a small restricted domain. So how can we use these insights for a better implementation? We can use the approximations and see them not as a burden and a source of error, but actually as an opportunity to save resources. And what we want to do is we actually want to explicitly increase the error on our implementation if it lets us to have a more efficient implementation. And additionally, we also want to specialize the implementation to a certain domain. Unlike the mathematical libraries that should work for a wide range of values, we only want to restrict our implementation to a certain predefined domain. And in this way, we are trading off some accuracy and generality for a more efficient implementation. Navigating such a trade-off manually is hard. So what we'll do is to make sure that the overall error in the end is still reasonable. We use sound verification, and to navigate the space of all possible approximations and their implementations, we'll use automated approximation. How do we specify our input? We create the non-executable real valued specification where we say for each input variable its bounds. And we also use the actual real valued algorithm as the code. Additionally, a user should specify the maximum error that can be tolerated by this algorithm. And given such a specification, our tool will generate a fixed point implementation of this kernel where each elementary function call is replaced by its polynomial approximation. Why do we do it for fixed points? Well, first of all, the are better suitable for specialization. And since we are trading off some accuracy, fixed point will allow to do it more gradually as there are more precisions available. And such an implementation for our example function saves about 50% of running time compared to the original implementation that is using mathematical library calls. So what is the challenge? There exist algorithms that can approximate elementary functions, for example, a Reines algorithm. The only problem is such algorithms require a local error bound, and a user only specifies a global bound for the whole program. And in this example, we already have 8 different elementary function calls. So we somehow need to distribute one error bound that is specified by the user among all possible error sources. And in our example, those are the approximation of 8 of the elementary function calls, and also the rounding errors on the implementations of those approximations that are not yet generated. So how does our algorithm deal with that? Our key insight was that the errors of the approximations should behave similarly to rounding errors and shouldn't be dramatically different in magnitude. So what we can do is we can abstract one elementary function call as a single sum source of error. And then we can distribute this global error budget specified by the user. And after that, once each elementary function receives its bound, we can decide which part of it will go for approximation and which part will go for the actual implementation of these polynomials. And now, given the approximation error budget, we can use Reines algorithm to actually generate the polynomial implementation, the polynomial approximation. So, as I said, we are abstracting away the errors by elementary functions as a single source. So if we say these behave similarly to rounding errors, there is already an algorithm that takes care of all the error propagation, diminishing, and magnifying the errors. And this is a precision assignment algorithm, any precision assignment algorithm. For our case, guided by static analysis, so it's sound. And our tool supports both uniform and mixed precision assignment. Of course, mixed precision gives you more leeway for the optimizations. As we can see, for our example benchmark, mixed precision assignment assigned at most 33 bits for elementary function calls. Now let's have a closer look at the cosine of the latitude 2. Since it received 33 bits, we can derive that the local error budget is 9.3 to 10 to the power of minus 10. And from this, we need to determine which part will be used for approximation and which for implementation. In advance, we cannot tell which distribution will be beneficial. So what we do is we split it equally and then call MetaLibM that internally implements Reines algorithm to get the best polynomial approximation. After that, we assign the precision to a generated polynomial such that the rounding error budget is satisfied and compute the abstract cost that estimates running time. I would like to note that this is not the worst case running time, but this is rather a relative measure that will allow us to compare different implementations of polynomials. And after that, we will try to redistribute this local error budget and assign less to approximation, more for final precision, and the other way around. And each time we generate the polynomial, assign the precision and compute the cost, and then choose the implementation with the smallest cost. For our example, that was actually the original equal distribution. And the assigned precision, again, we used the mixed precision assignment, used at most 35 bits for this cosine function. We repeat this process for all different elementary function calls, and then do a sanity check that the overall error actually is still satisfying the total error bound. With that, I would like to wrap it up and remind you that in this work, we soundly trade off accuracy for performance, and we do it by approximating elementary functions. For the distributing the error budget specified by the user, we use a sound precision assignment algorithm, and to decide which part will go for the approximation and which for implementation, we use a refinement loop guided by a cost function. On a set of benchmarks that we tried our tool, we've seen the average speed up over 2 times, and the implementation is a part of the tool DAISY, which is available open source, and I believe there is a link to the tool at the FPTalks page. And I would also like to note that there is a similar implementation for floating points, but I will not talk about it further. Thank you for your attention.
Very nice talk. So we've got a few questions here in the Slack. I think Ian, if you're keen, Ian has a question involving range reduction. Not sure if you want to do that one live, Ian.
Sure, put me on the spot. So, in your example, you're using the raw polynomials with your synapprox. I was just wondering how you handle if the input range isn't within what you can reasonably do for a polynomial approximation. Do you have some sort of like?
So I mean, this is.
Sorry.
Right. So you're asking if we're doing any range reduction or anything like this. I think we don't, because MetaLibM internally does implement some range reduction, but it's specific to floating points. And because we are dealing here with fixed points, we don't do that, but that would certainly be a possibility.
So you're using the MetaLibM example function scripts that they have? Sorry, this is a little bit too detailed.
I'm not sure what you mean example function script. So the tool itself asks for, so you specify the function and the input and the error bound, and MetaLibM itself generates the polynomial, but it's specialized to floating points. So it provides some guarantees that the error bound will also hold for the floating point implementation. But since here we are not interested in floats, but fixed points, we kind of have to do this part on our side.
Okay. Thank you.
So I think we are technically at the end of this session, but what comes next is a break. So the break can be a great way to not just brew some more tea to watch the rest of the talks and grab some kind of pastry, but also a good time to continue discussions. I know that there's quite a dynamic discussion going on with Santosh and Deevashwer about the previous talk, and I know there are more questions for this talk as well. So I'm going to keep the Zoom session open for the next half hour. Feel free to stretch your legs a bit and come back, but also feel free to keep talking about this, keep asking questions, and whether over Slack or here. And we will reconvene in a half hour at 9:30 Pacific time for Mark Dickinson's talk. So enjoy the break. And I personally am going to go brew some more tea.
I'm going to cheat. Anastasiia, One thing I was curious about, so there's some interesting stuff here that's like I guess thinking about your tool, it seems like it could be really useful for hardware design as well. And an interesting problem there might be what